Okay, so in first pass, what did today seem to be about? This endless trashing of reductive science and, you know, that's how you fix a broken clock, but the world of really interesting things are like broken clouds and are nonlinear aperiodic systems that are just as interesting and just as complex no matter what scale you look at them at. Hooray, most of science makes no sense whatsoever. Hooray for us, we are the vanguard. Okay, that's a drag because that really doesn't accomplish a whole lot, because what there has to be is a substitution. So where is the actual predictability? Where is the actual insight coming from? And that's what Friday is about, which is this whole field of complexity emergence, what we'll look at there. But the last point here winds up being, okay, terrific, you've convinced me you have trashed linear additive periodic systems and 500 years worth of books of science need to be burned at the stake. Is classical reductionism good for anything? Yes, we already know it is. It's good for when clocks are broken. No. I mean, is it good for anything in the realm of stuff that we're interested in how, like, biology works, in how behavior works, any of that? And what you get is it's very useful and very effective if you're not very picky, if you're not very precise. An example. There's some miserable disease out there that's wiping out people left and right, and it's this viral disease, and you're trying to figure out how to come up with a vaccine for it, and you finally come up with a vaccine, and you start distributing it to people, and what you see is exactly what Jonas Salk saw, was that it did wonders for preventing polio, but 1 in 560 kids instead would get a worse case of polio. So you could now ask a very reductive question, which is this vaccine, what happened in that one kid? And what we'll see at that level is, if you're trying to ask that, that's not going to be, if we understand what happened in that one kid, we're going to have to understand their individual cells all the way down and get better and better numbers, because it's, okay, we've just entered the world where it's actually a nonlinear chaotic system. Where's the reductionism useful? On the average, it's a whole lot better that kids got this vaccine than they didn't get the vaccine. You want reductive, classical, dead white male, reductive, predictable science. It's if you have a community of kids who get injected with this versus a community that doesn't, they're going to be healthier. Don't ask me about one particular individual, let alone one particular individual's immune system. The reductionism breaks down there. But if fancy, satisfying science for you counts as, do they tend to be healthier than them? Reductionism is great. That is sufficient. Suppose your question is, well, is there a certain time of the year? What's the weather likely to be in January versus in June? You are never going to have reductive tools that can tell you on any particular day what the temperature is going to be 3 years from now. But if all you want to know is, in general, it's warmer in June than in January, reductive tools that exist now are sufficient. And when you look at what people do in their research in the labs and places like this, in my lab, all of that, when you sit there and you say, whoa, we just learned when they're trying to like figure out the cure of some disease by finding the mutation, whoa, that's really a reductive approach, and we just learned that's gibberish. Whoa, everybody toss out what they do. It's actually quite useful because you're not very picky about what you want out of it. My lab, for example, studies what happens in brains after there's a stroke and trying to figure out gene therapy stuff that you can do. And we can't tell you why 1 rat out of 8 is not going to be helped by this procedure, whereas 3 rats are wonderfully so. Oh, I know, let's look at their single molecules. That's not going to do it. Reductionism breaks apart, but it's perfectly fine at the level that's useful here, which is, on the average, is this something plausibly that you might want to do to humans somewhere down the line? Most of what the science research is about, and when you look at the labs around here and you look at the labs you work in, if those of you, lots of you who do research, it's reductionism is a perfectly good thing to use because you're not being too picky. What you do not want to come up with an explanation for how every neuron in every developing grasshopper on Earth bifurcates at this point. You want to know, in general, somewhere around hours 3 to 4 after the egg starts or the grasshopper parents meet and fall in love or whatever it is, that in general, that's when you begin to get differentiation. Here, your science is great. So as long as most of what we're asking is this sort of science where you just kind of need to have a general predictive sense, reductionism is just fine. But nonetheless, underneath all of it, when you really want to understand the systems, it's anything but reductionism. And probably the most important philosophical point is when you look at these interesting complex systems, there is not the answer. There is not the solution to what is this water wheel is going to be doing, and thus all of us who are out there not quite matching the perfect one, it is not that we are deviating from what the real answer, what the real norm is supposed to be. The variation is what it's supposed to be. All of the things that are interesting when you measure them and they look like this, it's not because they are failing to be what they're supposed to be and match the norm.